Hi, I'm Bob. Welcome back to my solutions to the textbook Econometric Analysis, the 8th edition by Professor William Greene. Today, we will continue to solve the exercises from 10 to 13 for Chapter 3. Here is exercise 10. We note the sample variances of the variables n, d, and y. They are 1. We also have their sample means of 0. The sample size is 21. The question is about the regression of C on D. We need to find the sum of squared residuals. The idea is to see what elements are required to calculate the sum of squared residuals. Suppose the regression model of C on D is C equals D times B plus E, where B is the OLS estimator and E is the residuals. By the OLS estimator formula for one explanatory variable regression, B equals the sample covariance between C and D divided by the sample variance of D. We already know the variance is 1, but we need to calculate the covariance. On the other hand, the total sum of squares equals the regression sum of squares plus the error sum of squares. The error sum of squares is also called the residual sum of squares. Since the variances have 0 means, the residual sum of squares E prime times E has the following expression. The total sum of squares C prime times C can be computed from the sample variance of C. The regression sum of squares equals B squared times D prime times D. D prime times D can be found from the sample variance of D. So we need to find 2 elements for the answer: the sample covariance between C and D and the sample variance of C. Because C is the sum of N and D, the variance of C equals the variances of N and D plus 2 times the covariance between N and D. The covariance between N and D can be found from the regression of C on N. The slope coefficient on N is the sample covariance divided by the variance, so we obtain the covariance between C and N. Then we calculate the covariance between D and N, which is minus 0.5. Using it, we can obtain the sample variance of C and the sample covariance between C and D. These are the 2 elements to compute the residual sum of squares. Finally, we get the answer 15. We don't need to use all information in this exercise. Let's solve exercise 11. It is about computing the OLS estimator using matrices by the formula. Here is the OLS estimator in matrix form. We will do the matrix algebra in Stata instead of by hand. The first step is to generate the matrix X and the column vector Y. After creating a constant variable, we use the Stata command make matrix mkmat to generate the explanatory variable matrix X. We can list it using the matrix list command. Then we do the matrix operations to obtain the x prime x and the inverse of it. We generate the column vector y the same way. The vector y is a matrix with only one column. Next, we compute the part of x prime times y. Finally, we have the estimator vector b. We can verify that it is identical to the estimates from the regress command. To find the r-squared, we write down the definition. It is the ratio of the regression sum of squares to the total sum of squares. The residual maker, m0, converts the variables to deviation forms so that we can express the r-squared in terms of m0, x, and y. Returning to Stata, we generate the vector I, a column vector with ones. M0 can be generated with the identity matrix uppercase I and the column vector lowercase I. With all the elements in hand, we can calculate the regression sum of squares, the total sum of squares, and the r-squared. It is the same as that in the regression result window. Let's find the answer to exercise 12. There were two estimation equations. We are asked whether the results are correct. We use algebra to solve it. The log s divided by y can be written as log s minus log y. Rearranging the terms, we compare the two equations. It is impossible to obtain different coefficient estimates using the same sample and estimation method. The results are incorrect if the same estimation method is applied to the same sample. The estimates could differ if the estimation method or the sample size changes. Let's go to the last question. It's about whether the increase in the r-squared in a multiple regression when an additional variable is added to the model equals the r-squared in a simple regression with that variable as the only explanatory variable. We can write down the estimation model with two explanatory variables, x and z. Suppose z is the variable entering the model after x. According to equation 331 in the textbook, the difference in the r-squared between the multiple regression and the simple regression, delta, is as follows. The lowercase r star squared is the partial correlation between z and y, controlling for x. It can be further written in terms of z star and y star. Z star is the residual from the regression of z on x, and y star is the residual from the regression of y on x. Delta is the increase in the r-squared when an additional variable z is added to the model. On the other hand, in a simple regression, of y on z, the r squared is as follows. Usually, it is not the same as delta, unless x and z are orthogonal. If this is the case, x and z are not correlated, so the residual from the regression of z on x is z itself. We can also simplify the expression to show that they are equal to each other. Next, let me show you part C in Stata. In real life, it is almost impossible to find two variables that are not related. The trend variable must be related to the real GNP variable. We regress real investment on the trend alone and find the R squared. This is the R squared if the trend variable enters the model first, which is 0.01. Then we regress two models, the real investment on the real GNP and then the variable trend entering the model. The difference in the R squared is 0.76. We show that the two numbers are different. However, if the two explanatory variables are orthogonal, they are the same. We use simulated data to show it. We first set the seed and sample size. We can choose any number we like so that we can get the same sequence of pseudo-random numbers each time we run the program. We generate the error term epsilon, the explanatory variables x1 and x2. The data generating process makes x1 and x2 orthogonal. The R squared due to x1 is similar whether it enters the model first or second. Thank you so much for watching this video and finishing all the exercises for Chapter 3 with me over the past few days. See you soon in the following chapters. Take care. Thank you for watching this video and subscribing to my YouTube channel. See you next time.